Yeah, I'm Baarda, and so I'm going to talk today about a research project we've been working on for the past 3 years at Baarda, and we're just kind of getting it wrapped up here. So the topic of the presentation here today is soil sensibility and data utility, and really the whole story starts with soil sensors. So we've been introduced to electrical conductivity soil sensors, and they've been used in agriculture for a long time, but it's only been recently that the confluence of precision agriculture, GPS technology, and these conductivity sensors has given us the capacity to not only measure conductivity at one point in the soil, but to map a whole field in a relatively efficient means. And the whole idea behind these conductivity sensors is they give us a pretty good idea of what the soil moisture and the soil texture is. So we went ahead and we purchased two separate conductivity sensors. The one on the left there, that's the Veris conductivity sensor, and it's a contact sensor. So it has discs that penetrate the ground, sends a signal through the ground, measures the resistance, and converts that to conductivity. The EM38, the instrument on the right, it uses electromagnetic induction. So it creates an EM field, and as it moves along, it measures variability in that field and converts that to conductivity. So two different sensors and two different means by which we can detect conductivity in the soil. And as a bonus, the model of the Veris that we purchased had the capacity to measure pH as well as organic matter on the go. So the pH had a physical shovel that would dig into the ground, gather a soil sample, bring it up to electrodes, and it would measure our pH every minute as we went through the field. And organic matter was an optical sensor. So essentially looked at the reflectance of the soil. So darker soil would be assumed to be more organic matter, lighter soil, less organic matter. So why use soil sensors to begin with? Well, when we're talking about precision agriculture, we're talking about variability in the field, and we'd like to manage that variability. But before it can be managed, we have to better understand that variability. So two approaches to that would be, on the left, taking grid soil samples. So taking a sample every 5 acres and using that to come up with a better understanding of how our field properties vary over space. But one of the couple drawbacks to that is it's cost prohibitive, and it's not a very dense data set. It's tough to make predictions about the whole pattern across a field based on just 32 points. But when we talk about soil sensors, we can get as much as 50,000 data points in a field, and we can do that relatively cheaply. It doesn't necessarily tell us the same information, but the information we have is dense and it's very strong. So this slide, this kind of shows the patterns that we can get if we make an interpolation. So if we predict what's going to happen in the spaces between our samples, you can see the grid soil sample, that interpolation, it really doesn't look like a real world pattern. That's because of the challenges with a sparse data set. But if we look at the conductivity there, that's a more real world pattern, and even just visually we can see that that's a more effective means of describing variability, having that better data set. So when we looked at these sensors, we came up with 3 main research questions. The first was, what information can we generate? So what can the sensors tell us about the properties of the soil? Secondly, how can we use this information? So how can we apply this to become better farmers? And finally, is the information that we've gathered, is it useful or is it meaningful? So to start, what information can we generate? So there's really 2 things that the sensors can tell us. One, they can help us to better account for our in-field variability, come up with a better understanding of how our soil properties vary over space. And secondly, it may be able to give us some insight into the underlying soil properties. So what we did was we took both of our sensors and we passed them over 10 fields across the province, and each field was passed over at 2 times, so at spring and at fall, or as close to that as we could manage. In addition, we gathered any other data layers that we could get. So we got elevation maps, RTK, RTX elevation maps, as many yield maps as we could get, and in a few instances we were able to gather UAV and DVI maps. So Toby was pretty tired by the end of this project. It was a lot of work for him. I was thinking of putting a Bill 6 joke in, but I didn't really want to touch it. So this is all 15 data layers all put together, and it's a ridiculous amount of data. So we had to come up with some way to summarize it, to make all this data a little bit more digestible. So we decided to come up with an appropriate scale at which to sift through this data. And what we chose to do is we chose to go by
a cedar width. Because a cedar width, that's the smallest scale at which we can make a meaningful response to this variability. So if we define variability any smaller, we can't really make a management response to that. So it doesn't really make sense to be any more precise than a cedar width. So this is a grid that we've overlaid over the field, and each square is based on the cedar width that the cooperating farmer was going to use to manage variability. We took all of our data layers, all the layers that we had, and we nested them into this grid geography. So for example, we've got elevation here, we've got a yield map, and again, we had 4 different yield maps for this field. Here's an example of a Varus EC map. And again, we had a number of different conductivity maps. Now, if I toggle back and forth between the yield map and the EC map, visually you can see there's some comparison, there's some consistency in the patterns, and that can be misleading. The visual patterns we see, I mean, our brains are programmed to recognize patterns, and in this case, that can mislead us. So it was important to come up with a statistical means to measure how well those different maps related to each other over space. So creating this grid geography gave us the capacity to do that. So we could take all our data layers, layer them on top of one another, and we could pick out any one grid square, and we could identify what attributes were attached to that. So what was the measurement of EC in spring of 2013 with the Varus? What was the pH in this grid square? What was the the yield in 2013? And not only can we do this on a one-to-one basis, we can look at how those patterns relate to one another as well. So how similar is the pattern of yield in 2010 to the pattern of EC measured by the EM38 in the spring of 2014? So each pair of data layers we can compare, we can measure how similar their patterns are. Which leads us to the next slide, which is a correlation analysis. So we took each pair of data layers, compared them to one another, and came up with the strength of the relationship. So how similar the patterns were between data layers. So here's our correlation matrix, and it's not important to really delve into all the details. I'll kind of highlight a few things. So this first square I've identified, this is where all our EC layers are compared to other EC layers, and we can see that all those relationships are strong and consistently strong across the board, which means that our EC maps, those patterns didn't change over time, they didn't change across sensors, and we saw the same pattern in all 10 fields that we went through. So those EC measurements are highly consistent and highly repeatable over time. This column, this is the elevation, and we can see that in some cases there's relationships that are positive or negative, but I just wanted to point out that elevation seems to be an important factor, although it may be kind of tough to flesh out exactly the implications of that. And finally, the last 4 columns on the right, that's all 4 of our yield data maps. And you can see, I found it really interesting that there's some relationships for 2 of the years, so yield in 2010 and yield in 2013, the two outside columns in that last square. You can see there's some strong, or at least moderately strong relationships with some of the mapped layers that we took. But 2 of those yields don't really have relationships at all, and that really shows us how variable our yield can be from year to year. I think, even myself, you tend to think those yield patterns are pretty static. They don't change over time, but really when you look into it, there's quite a bit of variability from year to year, and influences on that, like weather's probably a big one, management practices, crops grown. I mean, there's a lot of moving parts. So if we dig just a little bit deeper into this, that top blue square, that shows where yield is related to conductivity maps. And conductivity doesn't look to give us a lot of insight into the pattern of yield directly. And the bottom square is yield relating to yield. And again, there's not a lot of strong relationships in the pattern of yield from year to year, which is pretty interesting, I think. So the key points from that is our EC data is highly consistent. It's consistent over space, it's consistent from one time to another, and it's consistent regardless of what instrument we use to measure it. And secondly, our spatial patterns of yield can vary significantly over time. The relationship between yield from different years isn't always strong, and between yield and sensors isn't always strong. And those relationships do change from time to time, from year to year. So now that we've looked at how our sensor data relates and describes variability in the field, we wanted to look at what our sensor data can tell us about soil properties in the field. So we compared our map data to soil samples that we had taken in the field and looked at what relationships are there and what that might tell us, what kind of information the sensors could give us about soil properties in the field. So we can divide this up. It's the same format as the last chart. We can divide it up into three main sections. So this first one is where conductivity related to soil texture. So our conductivity measurements were highly accurate at detecting the presence of clay and the presence of soil moisture, which we knew going in, but it's always good to kind of have that backup and to know that those measurements are consistent over time and they're consistent across all 10 fields that we had. The second section is how well our macronutrients, so our N, P, K, and S related to our map data. And we can kind of see there's not a lot of strong relationships. So our EC measurements didn't directly tell us, what the levels of those macronutrients were at those locations in the soil. And finally, we kind of have, so we've got organic matter, cation exchange capacity, and pH in this section. And this sort of speaks a little bit to the capacity of the soil to make nutrients available to crops. And the design of this study didn't really allow us to dig deeper into this, but there's definitely some relationships there, and I think that's a direction worth looking into if we can map, that property of soil, and because it would have real implications for crop growth. So the key points out of that section is EC correlated strongly to texture and moisture, but didn't necessarily have relationships with our macronutrients. So our first question was what information can be generated? Well, we know our soil sensors are highly consistent, and again, sensor to sensor, they're consistent across space, and they're consistent across time. So we can expect a reading at one time to be repeated at another time with another instrument. We can highly depend on this data. And EC is a very strong indicator of the presence of clay and soil moisture. But we didn't find a lot of strong relationships between conductivity and either yield or soil nutrients. So we know what this data can tell us. So how do we use this information? Well, we developed a research trial, and what we did was we divided the field up into management zones on the basis of different data layers. But there's a few questions we wanted to ask first, and in order to do that, we needed to know what are the best data layers to use, and what is the best way to turn that data into management zones. And we wanted to be objective in this. So I've got a map here. This is our EC map before. And I subjectively divide it into zones. I took all the data, divided it into 5 equal sections, and drew a map. But I have no way of knowing whether those zone boundaries are meaningful or whether they're useful. And we wanted to come up with a way to objectively decide that, to have something else tell us that our zones that we've described are meaningful. So that means identifying zone boundaries and choosing the right number of zones. So to identify the key data layers, we went through a process called principal component analysis. And really what this does is it takes all our layers of data and looks at how they vary over space and how those patterns relate to one another. So it summarizes those data sets. So if we have 5 data layers that their patterns are highly similar to one another, they're really contributing the same thing to our understanding of our overall variability. But if we have data layers that have different patterns, they're contributing something new to our understanding of field variability. So they'll load up on a separate factor. So at the end of the day, we went through the process and it identified 2 factors as being the key factors among the data that we had that help us understand variability in the field. The first was conductivity, and the second was yield and organic matter. So we made sure we focused on those 2 layers. So EC and yield as our key data layers. That's really the key out of the principal component analysis. So the next question was, how do we objectively define zones? How do we objectively determine what the boundaries are between zones? So in most cases, our data will conform to a normal distribution. So it's something we can expect the distribution of data to be. And if we divide it into 3 equal sections, we're going to get a result that we can expect to be repeated over time. But sometimes we have data sets that don't conform to that distribution. And if we divide it into thirds, we might have divisions that aren't meaningful. So between the red and the blue zones, or the red and the green zones on the right, that division comes right at a whole bunch of data that's highly similar to one another. So that's not really a meaningful division of zones. So we needed to come up with an objective way to define that, to avoid this process. So what we used was what's called k-means cluster analysis, and it's commonly used in soil science, and it's a way to objectively determine what is the division between zones. And not only can it do it for one layer of data, it can take multiple variables and cluster them based on how similar they are on different properties. So here's kind of an example data set, and here it is divided into zones, again, objectively. And what it's done is it said, I've got yield on the y-axis and conductivity on the x-axis. So all the data points that had low yield and low conductivity were in one cluster, high yield, low conductivity in another, and then high yield, high conductivity in the green cluster. So it'll run through the process, it'll build zones by 100 different ways, and it'll test them. And it'll test them by minimizing the distance across the cluster and maximizing that distance in between clusters, so that we have an objective measure to know how effective the process has been. And in addition to determining effective zone boundaries, we can also determine the effective number of zones by the same process. So we run through it, we try 3 zones, we try 4, 5, 6, as many as you want, but we only went up to 6. And it'll divide it into zones and take those same measurements. So it'll minimize that distance within the clusters, maximize that distance between clusters, and it'll tell us what's the best way to go. Is the best way to divide this data, is it 3, 4, 5, or 6 zones? So instead of having our zone delineations looking like this, we might have something a little more meaningful that looks like this, or even 2 zones that might look like this. So really, at the end of the day, the point of that whole process is that we've defined zones by a mathematical process. It's objective. We haven't made those decisions, and that means that if we go to another field with another data set, we can expect the same results. We've got some consistency built into the system. So now we built zones by 5 different methods, and I'll kind of go through them one by one. So we focused on yield and on conductivity, because those were factors that were identified as key factors. And we also added in some surface geography and grid soil, just to have a bit of a baseline to see how well our key variables compared to other strategies. So the first was surface geography. Now this, really it was the most basic, most simple way that we can identify variability in the field. It's as simple as looking across the field and saying, these are the physical features that I can visually identify, and using a paint program to draw zones over top of those features. And, excuse me, all 3 zones were then nested into that grid geography that we used at the start. Grid soil samples, we took a 5-acre grid sample, and so every 5 acres took a soil sample, and we measured the amount of nitrogen in the top 6 inches of soil. We ran an interpolation to predict the pattern of that nitrogen across the field, and we nested that into our grid geography. Historic yield, we took all the available historic yield maps, and before we could combine them together, we had to clean that data, which means at any place where the combine runs empty, that's a bunch of zeros that's going to throw off that data. So we had to clean out anything that didn't make sense that way. And in addition to cleaning it, it had to be normalized. So that allows us to compare the values, yield values from canola to wheat to barley, so that they're all the same. We can compare them, add them together, and we came up with a historic yield map, or zone delineation. Conductivity, the k-means cluster analysis identified 2 zones as optimal. And composite, we did the k-means clustering with both yield and conductivity. And this is the delineation that came up with. And I'll just toggle back and forth a little bit. You can identify some consistency in patterns there, especially in the yield NEC. You can see the contribution of both yield and conductivity to the outcome in that one. So our question 2 was how can we use this information? Well, there's 2 key things. There are processes we can use to objectively determine what are the key variables. And for us and across all our fields, conductivity and yield were identified as key variability, or key data layers that helped us understand variability. And there's also a process by which we can objectively determine the number of zones and the boundaries between zones. And again, that objectivity allows us to have something that we can expect to be repeated. We can expect the same results under different conditions. So finally, is this information meaningful or useful? So we've created zones, and we'd like to know how effective those zones are. And there's two ways that those zones might be effective. One is that if they identify regions of different levels of productivity. So do they identify regions that yield better or worse than other regions? And secondly, do they identify regions that respond differently to nitrogen? So we built a research trial. So we had all 10 of our fields, we built in a variable rate nitrogen trial. So we applied different rates of nitrogen across the field. So 0, 75, 100, 125, and 150 pounds of actual N. Oops. And then we took our zone, so that's in there on the ground. And each of our zone delineations, we can overlay that on top of our nitrogen trial one by one. And this strategy allows us to compare different zone delineation methods and how effective they are. So if we look at surface geography, one zone at a time, so we'll look at the blue zone. So here we can select all the area where we applied 0 pounds of nitrogen in the blue zone, and where we applied 75 pounds of nitrogen in the blue zone, 100 pounds, 125, and 150. So we know the yield response under 5 different rates of nitrogen within each zone. And it allows us to come up with a response curve that looks something like this. So when we take all 3 zones, we come up with 3 different response curves. So I talked earlier about there's 2 things we're looking for to differentiate, to know whether or not these zones are meaningful. One is their average yield. So that would be, if you've got 3 curves, that would be the gap between the curves. So do they identify regions of different levels of productivity? And the response, that's how yield responds to increasing rates of nitrogen. So that would be the shape of the curve. So ideally, if the zones work out perfectly, we'll see 3 different levels in the curves, and we'll see 3 different curve shapes. So grid soil samples, there's not a lot of differentiation between those curves. They're pretty much, the means are pretty much at the same level, so we probably haven't identified meaningfully different zones. And again, the responses, particularly for the blue and the red curve, they're almost identical. So really, I would call this that we weren't successful. The historic yield, on the other hand, we've clearly identified zones of different levels of productivity, and the statistics back that up in this case, where we've got that stratification. We've got 3 different levels, but the shape of those curves are almost identical. So even though we've identified zones of different productivity, we have not identified zones that might have a different response to nitrogen, that might be able to be managed differently from a nitrogen standpoint. Conductivity, same thing, we've got some differentiation and maybe some difference in curves. And composite, again, we've got some differentiation in productivity and maybe some in the response. So the next step was so this table is basically a summary of what the results were across all 10 fields. And really what I'll kind of get you to focus on is the red section. So the red section is the instances where we had 0 success, where from the standpoint of identifying zones of different levels of productivity, different yield means, we had no success in 20% of the time for the first 3, so for surface geography, grid soil sampling, and yield, 30% for EC. But our composite, we always had some level of success. So we never had a complete failure in identifying zones that were meaningful based on their productivity. But from a response standpoint, it's a different story. We had very little success in identifying zones that could be managed meaningfully differently based on nitrogen, or based on yield response to nitrogen. So to come back to point 3, is this information meaningful and useful? Well, yeah, we've been able to identify zones of different productivity with soil sensors, and I think that's a pretty big win right there. But we had limited success in being able to differentiate management strategies, especially in the context of variable nitrogen. So to conclude the whole thing, we'll start from the very beginning. We figured out that soil sensor measurements were found to be highly consistent, and really it's a really effective tool to better understand soil variability in the field. However, we didn't find any obvious correlations between EC and soil nutrients. There's not a direct relationship there. There's certainly implications, but not a direct one-on-one relationship there. And that's because EC is really just one piece of a pretty complex puzzle. and variability in weather over years or management over time can kind of have an impact on those relationships. So at the end of the day, every field is different, and the relationship between our sense data and soil properties, as well as yield, can vary quite a bit over space and over time. And I think the key message from this whole thing is that variable rate technology requires a variable approach. So what's good in one field might not be good in another, or what works in one management system may not work in another. So if it's a technology that you're getting into, be prepared to tailor a specific strategy for specific fields. And at the end of the day, the process is as important as the results. So there's a lot of different strategies, and we had varying levels of success with different strategies in different fields, but they're all testable. So anything that is tried, we can go back in and make an assessment on how well it worked. So yeah, at the end of the day, there's not really a cookie cutter approach. There's not one magic formula that's going to tell us how to manage variability in our field. It changes from field to field. It changes from year to year, but we have the tools to understand those changes better. So, thank you.
Thanks a lot, Lewis. We have time for one question. Is there any questions?
Sorry, the question was where are we going from here? I think we've learned a lot in the process of this study, and I kind of said at the end, the process is as important as the results. So we really learned how to better understand field variability and at a manageable scale. So one part of the answer is that we certainly have the tools to do more research. We certainly have a better understanding of the whole understanding variability, precision ag world. One of the things that I think would be worth looking into, so we saw some relationships between our sensors and the soil's capacity to make nutrients available, but I'd like to better understand those relationships. So maybe that's something. We're looking at just one piece of the puzzle here with conductivity, but I think there's a lot of different ways to understand variability that may have implications. I think the UAV side of things, there's a lot of buzz over there. I'd like to look into that. Does that help us understand variability on a different, with a different measurement? So I don't know if that answers your question, but I think there's a lot of potential, and we certainly have the tools to go in there and test whatever's out there.